Hey guys, welcome back to part 3 of AP Physics C Mechanics, Newton's Laws Review and Practice. There are 4 more problems, multiple choice, and I'm going to finish them rather quickly. So, number 10, the pulley system above requires a person to pull on the rope with a minimum force F in order to lift the block of mass M. An inclined plane of angle theta requires the same force F to push the block up the ramp. Assuming ideal conditions in both situations, what is the value of theta? Let's look at the first situation. If you recall, there's a formula for the force applied. It's called the effect force. It's basically the force that is applied, the force required to lift an object, which is the weight of the object divided by, in a pulley system, divided by the number of ropes that are supporting. So in this case, it's 1, 2, 3, 4, 5, and 6. So the force equals mg divided by 6. And that same force is actually on a plane, on a, an incline. So you have the object, and then you have the force applied, F, and you have mg sine theta. So sine theta. So the net force is equal to, assuming up is F, up the plane is positive, x direction, F minus mg sine theta, and that's equal to 0. Because it says assume ideal situation, and it's an inclined plane on an angle theta requires the same force. So if it requires the same force to push it, obviously any more force will push it up and accelerate it, but just enough to overcome the initial force of friction. So F equals mg sine theta, and it wants theta, so we can solve mg over 6 equals, we can substitute mg sine theta, and the inverse mg cancels, and you get theta equals inverse sine of 1/6, inverse sine of 1/6, which is equal to 9.6 approximately. A 60 centimeter rope is tied to the handle of a bucket, which is then rolled in a vertical circle. The mass of the bucket is 3 kilograms. At the lowest point in its path, the tension in the rope is 50 newtons. What is the speed of the bucket? At its lowest point, you have the circle. Here's its center. The lowest point, there's a bucket. Okay. Tension points towards the center of the circle, as that is the centripetal force that provides the centripetal acceleration, which keeps the object in circular motion. The tension and the weight of the object is also in play and counteracts the tension in this position and actually is opposite to it. So let's assume that up is positive, and this is very important assumption. At the lowest point in the path, the tension is 50. What is the speed? We know that the net force in the y direction at this point is equal to the centripetal force, which is mv squared over r. And we know that this is 50 minus the weight, which we can round to 30 newtons. And therefore, the centripetal force is approximately 20 newtons. And the velocity is equal to 0.6 times 20, which is 12, divided by the mass, which is 4, times this, you take the square root, you get 2. So 2 meters per second. So 11 is B. 12. What is the critical speed below which the rope critical speed below which sorry, I was just drawing on this. What is the critical speed below which the rope would become slack when the bucket reaches the highest point in the circle up here? And basically, we know that that we want V, and V is defined as the critical speed below which, so anything less than V less than V critical, where V is the speeds when the tension would equal 0. Right? Obviously, if we spin it like 0.0003 meters per second, for instance, you could pretty safely assume, based on intuition, that the rope is not going to be taut and there's going to be no tension, therefore, and it will slack. So we want when tension equals 0. We know that the bucket, we know that the weight, the tension force points towards the center. We also know that the weight points downward as well in the same direction. Both of these are negative. The net force equals minus T minus W equals mv squared over r. We know the tension is 0 because we want that I mean, this is the minimum velocity, right? So any velocity is greater than this, the tension will be, well, there will be some tension. Any velocities below this, so this is the critical speed. So we want negative WV over m, and technically we can make r negative, so this becomes positive. Also, we can't have the velocity is actually tangential, and it'll either point right or left, doesn't matter. It wants the speed, so it's the magnitude anyway. So basically you have the weight, which is approximately 9.8 times 3 times 0.6 divided by 3, and then you take the square root and you get around 2.4, and the answer is C there. Okay, last problem, question 13. An object moves at a constant speed in a circular path. Another circular motion problem. With a radius of r at a rate of 1 revolution per second. Now we know that that's actually omega, but if we think about this, we don't even have to bring in rotational kinematics, because we know that 1 revolution is actually 2 pi r. So we know that the object travels 2 pi r in 1 second. Therefore, that's the speed, and we know that the acceleration. Well, if the speed's constant, that means that v's constant, which means that a sub tangential acceleration is 0, and we know that the acceleration actually points, I don't know how to draw this, right there, a sub c. So we know that the acceleration has 2 components in circular motion. We know it has a centripetal component and a tangential component, and we know that since the tangential component 0, the acceleration is c, is just a sub c. So it only has centripetal acceleration, because we know that if it had tangential acceleration, then aka acceleration tangent to the circle, the speed wouldn't be constant. It would actually be increasing or decreasing. So a sub c equals v squared over r. V squared is 4 pi squared r squared divided by r. 1 r cancels and you get 4 pi squared r. That's why the answer is D. Thank you guys so much for watching, and stay tuned for the next unit, which is work, energy, and probably something else.